Section 2.3, Measures of Spread. The goals here, want to find the range of a data set. We're going to compute the variance and standard deviation of a data set. Two very important concepts in statistics. We're going to look at understanding percentiles, and then to finish it off, we're going to do two things that are related. We're going to compute the 5-number summary and IQR, and then we're going to draw box plots. And this will be one of the final places we'll see graphical displays, but we needed the median concept before we could do this one. So that's why it's showing up here. So in this section, we'll look at several ways to express the spread of a data set and some ways to measure position within a data set. So why should we care about measures of spread? Well, the location of center can only tell so much about a data set. Consider the following. We've got these two different sets here. One of them, 4 5s. The next one, 1, 3, 7, and 9. Both of them have a mean of 5. And if somebody just came up to you and said, hey, I've got two data sets here. The mean for both of them is 5. You might start thinking, oh, then they're probably similar to each other. And they might even be the same numbers in each of the two sets. So the issue here is that you might think that these two sets are the same based on just the mean. And that's a problem, because you look at the sets and they are not the same. So if you included a measure of spread with the mean, you would know that the two sets were different without having to look at them. If you look at that first set, there's really no spread at all. And we'll see the range here shortly for that first set would just be 0. And then the second set, we'd say, oh, the range, it's going to end up being 8. So when you start looking at that, it's like, okay, they both have the same mean, but one has a range of 0, the other one has a range of 8. That gives you a better picture that, even though they got the same mean, there's something different between them. One has, when you ever see a range of 0, all the numbers are the same. And the other, knowing it has a range of 8, that there's a spread in that data more than that first set. So, the spread of a data set is really important for getting a better picture just from the numbers that are given. So coming down here then, for the range, it's the first and most basic measure of spread. And to find the range, you just need to know the minimum and maximum data values. So let's see if I can write better in there. There we go. Once you have those, the range can be found by doing the following. You just say, oh, well, what's the range? And the range is just equal to the maximum minus the minimum. That's it. It's one number, the max minus the min. So to find the range of the following data set, go ahead and do that. Pause, take a second. Okay. So one thing that people typically do with this to get it wrong is they just do 9 minus 2 because you assume data sets are always going to be in order. I did this purposely to throw you off because I want you to be careful and make sure that you do truly look for the high and the low. In this case, the high would be 9, the low would be 1, and the range then is equal to 9 minus 1, or 8. So just a single number value for the range. Okay, so that's a basic one. That's all you got to do. Subtract high minus low. Make sure you don't get sucked into the easy thing of just picking the first number as the low. Always look for, through the data set if they're not in order. And what we're going to look at now is variance and standard deviation. So the standard deviation is the most commonly used measure of spread in statistics. It shows up all over the place. And it can loosely be thought of as the average distance of each data value from the mean of the data set. And you'll see when we start looking at the formula, there's this idea of average in the formula. And we can think of this as just the average distance, average difference even, of each data value from the mean. So in general, if you do happen to find the standard deviation, it's going to be a number. And then if you add it to the mean and subtract it from the mean, more than half of the data values in the set will be between the two numbers that you got. So visually, if you have your little number line here, you got the mean, and then you say, okay, well, I'm going to do mean plus the standard deviation. After you calculate it, you'll get a number over here on the number line. And then if you subtract the standard deviation, you'll get another tick mark to the left, same distance away from the mean as the tick mark on the right. Standard deviation is going to be the same. So half of the data values would be between these two numbers. So in whatever set you're working with, you find the mean of the set, you find the standard deviation, you take the mean minus the mean plus the standard deviation, and if you go back and look at that data set, you would see that typically more than half, sometimes much more than half, lies between those two numbers that you found doing that subtraction and addition. Okay, so how do you compute the standard deviation by hand? Well, thankfully, we're not going to do this really by hand in this class. I'm going to show you how to do it on Desmos here very shortly. But there are two forms that you have to be aware of. Even if you're doing it by hand or technology, you got to make sure that you understand which type of standard deviation you're looking for. And there's one that comes from a sample or one that's based on a population. And remember, samples and populations are different, and we treat them differently in statistics with a lot of the calculations we do. So sample standard deviation, it's the square root of the variance. So this is how that variance concept I mentioned relates. They're basically the same formula to get there, except you take the square root of the variance to get to the standard deviation. And as I said, it's roughly an average distance that the data values are from the mean. And the symbol for standard deviation in a sample is S. And I mentioned that in a prior section as well. The formula for the sample standard deviation is this. And what we see here is that the S is the standard deviation, S squared is the variance. And I'll mention this a little later in the notes, but S squared is the variance, and you take the square root to get S. Squares and square roots cancel each other out. And then you got this beastly formula here. Remember that sigma symbol, capital sigma here, looks like a sideways M. That is the sum symbol. So we're going to add some things together in the numerator. It's where that average distance idea comes in. And in math, when we start looking at x minus x bar, we have a fancy word for these x minus x bar, data value minus a mean. So the deviation is a fancy name for that, and that's why they have standard deviation. When you deviate from something, you're different. So it's a very logical use of the word, deviation, but the deviation here is x minus x bar. And you would do this for every data value in the data set. You find the mean first, and then you do data value 1 minus the mean to get its deviation. Data value 2 minus the mean to get its deviation. Data value 3 minus the mean to get its deviation. And you keep doing that until you run out of data values. So what they've done up here is they're going to sum together all these deviations squared. Well, why the square? Why are they squaring this? Well, if you do a bigger number minus the mean, you'll get a positive value, but maybe, when you find the mean, there's going to be numbers that are smaller than the mean in your data set. That's just the nature of how data works, and means how they work. Well, if you do that subtraction, you're going to get negative numbers. And in fact, if you didn't square it, you would get a bunch of positives and a bunch of negative deviations that if you added all the deviations together, just with their signs in place, you would get up to a value of 0. And it's like, well, okay, how does that help me? It doesn't. So what the statisticians did as they were developing this formula is they said, all right, since we add up all the deviations, we get 0, we need to do something more with this. So what they did is they squared the deviations to make them all positive. That's why they have that square there. And when they square the deviations to make them positive, essentially what they're doing is they're taking all these differences and squaring them. And that avoids the issue of getting a 0 when you add them all together. Because when you square them all, make them all positive, you won't have negatives canceling things out. So you do the x minus x bar, the deviations squared, and then you add them all together. And that's that average part of the standard deviation. You're adding together a whole bunch of things in that numerator, all the deviations squared. And then you divide by n minus 1. I'll talk more about that here in a second. But by dividing a sum, again, alarm bells should be going off like, oh, hey, that's an average. You add things together, divide by the total, and you get an average. And here they're dividing by 1 less than the total amount for a reason I'll, again, get into here in a second. So they add together all those squared deviations, they divide by n minus 1, and then they also realize that by squaring a number, you change its nature. Like if you take the number 2, you square it, you get 4, makes it much bigger. You take 1/2, you square it, it becomes 1/4, becomes smaller. So in order to fix that, they took the square root of the entire result. And it's not a perfect mathematical thing in terms of, oh, it's just undoing the square. There's more to it. But this is what statisticians settled on as being an acceptable way to get this standard deviation calculation. So why the n minus 1? Why aren't they dividing by n, the little n? And technically they call this a degrees of freedom. You won't see much of this in this class. You would see more of it in a intro stat class, and maybe even not so much then. You deal with a lot more in higher level stats. But basically it helps make S approximate the population better. And that's your goal. You want the sample to approximate the population as best as possible. And when you start including degrees of freedom into the mix in the statistical calculations, it helps approximate things better. So that's all that's really happening there. So, don't panic. It's just part of the formula, always will be part of the formula. And if you think about you're dividing by 1 less, when you divide by something smaller, it actually makes the result bigger. And a lot of times with samples, your standard deviation, if you didn't do that, is going to be small compared to the population's true value. So they give it a little bit of fudge factor by taking 1 away. And it's enough to make the numbers work out a lot better. So I'm going to go ahead and pause this video, or actually stop this video, and then we'll pick up with the part 2 looking at the population standard deviation.